Morning to you. So in this lecture, we will prove the main result of this lecture is actually to establish that countable union of countable sets is countable. This is the main result of this today's lecture. And for that, we will first establish an important result which characterizes the which gives you alternate definitions or equivalent definitions of a countable set. You have now three definitions of a countable set. These definitions are provided by the following theorem, and which states that if you have a non-empty set, then these three are equivalent. If X is countable, if and only if there is a surjection from set of natural numbers to the set X, and that is equivalent to saying that there is an injection from G to there is an injection G from X. Where establish the equivalence of these three results, with first proving that implies 2. We suppose that countable set, and when you say that X is a countable set according to definition of a countable set, it is either countable infinite, it is either countably infinite, or it is finite. So begin with this first. If it is equivalent to the setup, then it is equivalent to set of natural X. This is by definition of surjection, because by definition surjection. So in case of finite, we will always is when this countable set X is a finite set. Finite such that a set is finite. If the empty set equivalent to the set, the first natural and given to us that X is not empty. So in case it is, we will have this X to be equivalent to some nk, and equivalent to n of first natural numbers to X. Now, but we require a surjection from n to X. We will this surjection nk to natural numbers defined by this following function. How it is being defined? Let me do. This is n, and this is X. Okay. Already at H from X, and in X, each element has a pre-image. This is a surjection. Each element has a pre-image in NK. What we intend, we want a surjection from N to X. I have written a notation X N to X. The notation has to be N to X. Reach this surjection. Suppose you have these remaining elements for which you want to get elements, images for these elements, this region we want to. So what we are going to do, I'm going to fix an element here. Suppose this element is h of 1, and then everything from this green dots, I'm going to map everything from here to this h1. This way you get a map from set of natural numbers to X, and clearly by definition this is surjective, because no element in X is such which do not have any pre-image under this new function H. So Actually, there I need to change the notation F. So we have the surjection in case finite x is finite. We have a surjection again, and this constructed or extended from the distinct surjection which was defined on the set of first k natural numbers. So in this way, we get this through this second have always a surjection from x. And now we will establish 2 implies 3. And in 2 implies 3, what we have a surjection from natural numbers required to find an injection n. And how we are going to define this is how we are defining an injection g for every x in x. We are defining g of x to be the smallest element of the set of under f. Uh, each x always has edge under f. This is surjection. So that implies that this is non-empty. This set is non-empty. If this set is non-empty and this is a non-empty subset of uh, we already know what tells us that every non-empty subset of natural numbers has a smallest element that is also called the least element. And there is a result which says this thing that is known as, and it is very obvious that in x that has to be accepted. That's a kind of axiom also, well ordering principle. But this is known to all of you that an empty subset of natural numbers has a least, giving that least element uh, to be a image of x, and this g is a well-defined function. Why it's a well? Because e of x, the images is a non-empty, so g of x is definitely some natural number. Now we establish that this one function. This is the required thing. Now we choose 2 distinct elements in this set X, and we will show that they have the distinct images. But let us look. You are choosing to be distinct elements, and then we claim that these sets have empty intersection. They do not have empty intersection. There will be some element which is common to these. So this implies that n belongs to inverse of x and of f inverse of y also. In the inverse y also. Now by definition of this inverse image, this implies that image of n under f has to be x, because n is an element of this set. And similarly, when you apply the definition of when n belongs to this set of pre-images, now this your definition of a, because here you have n, and if x and y are distinct, then n is going to have 2 images, which is against the definition of the function, because every element has a unique image. So this gives control is of x and y under f to be non-empty, and hence this has to be empty intersect. To be empty, this has, and these 2 sets different list elements. They cannot have the same list element because list element lies within the set, so they cannot have a list element. So they will have a distinct list element, and the element one by g, one is a image of g of image of x under g, and another is a another list element of this set of images image of y under g. So these images are going to be there, and this way this establishes that this G is a 1 1 function, and this also this proves that 2 implies 3. Now finally, to complete the proof, we and in 3 implies 1 we have to according to 3 we have an injection from x to n. This is an injection from x to n. This implies that this is equivalent to g of this is g is an, and but what is g of x is a subset of n, and hence g of x is a countable set. Subset of a countable set is countable, and a set equivalent to a countable set has to, hence this x countable set. So and this completes the, with this we get the to complete the cycle of these this equivalence, and hence the proof of the theorem. And this proof of this theorem is going to be vital and a very important result in establishing this final result of or say which states that the countable union of countable is a countable set. Let us take a countable sets, denote this family of countable sets. Each set in this family is a countable set, and since the family is a countable, so J is a countable, which is through which we are indexing this family. And when J is countable, so J is either equivalent to set of natural number is either equivalent to nk, or it is equivalent to set of natural numbers. So without loss of generality, we n. So also we are going to suppose that each element, each set in this family is a non. That will not change our result, because and empty set will have no contribution in the union. So better to take each set as a non-empty set. Now each xn is a countable set, and by our result that we just proved, and choose a with f sub n is to also j is countable, so we will have we can also choose another surjection from n to j. So we have these surjections, and using these h from n cross n to this unit, this definition, and this is a well defined natural number. G of I is an element of G of I has to be sum of rejection defined. Why this H is a surjection? Why this is a surjection? And we here, and by definition of the union, X is in some element Xn. And now looking at the using the choose a natural number I such that in of each n is section. Surjection defined on Xn is f sub n. I added it sub gi because gi is equal to n, and but this surjection, so I am another element, another natural number in n, whose image under Fn is x, because F is a surjection from numbers to xn, and x belongs to xn, so xn will have a pre-image, and let that pre-image be j is equal to x. Now clearly, if you look at this element pair now I and j, you have been able to find I and j, and then this ij belongs to the n cross n set. So, and look at its image. By definition, its image has to be hi of j has to be by definition it has to be f of g of I of j, and look at here, this is equal to x, and this establishes that this h is a surjection, not bijection. We don't need to prove it bijection, and bijection, but it is a surjection for sure. So this establishes it's a surjection. Whether not, it's a little bit of work to do. Now what we have this, if you look at this diagram now, from n cross n to this union family, we have a surjection H, and we better know that this n is equivalent to the set of natural numbers. This is what we have done already, because it is a countably infinite set, so it has to be equivalent to set of natural numbers. So we will have a bijection, and let that bijection be phi. So we have a bijection from set of natural numbers to n cross n. So now, if you compose these functions as shown in the diagram, this is the path. We get a function from set of numbers to this union, and let that function is at phi position 1 1 function. It is a bijection, so it's a 1 1. It is surjection. The injection is always a surjection, and hence this from n to this union is a surjection. Thus, finally, we got a surjection from n to this set union, this family of sets, and by the previous theorem that we just proved, from that theorem, it follows that this union is a countable set. And what we had to prove that this union has to be a countable set, and this establishes that countable union of countable sets is a countable set, and this set that we had to do, and then we will go now to the in detailing about this set of real numbers R. So if you have any